excitation, what is their position of Fermi level. So now we are in the stage to form PN junction of these two by making contact of these two semiconductors. Okay, so before that I start PN junction, there's one more important thing, transport mechanism. Okay, how charge carriers conduct electricity or conductivity, how conductivity is come in semiconductors. Okay, so there are basically two mechanisms. One is we have already discussed, that is called drift mechanism. Okay. So you have a number one is drift mechanism, and all you know what is drift mechanism. Okay, movement of charge carriers, movement of charge carriers. Okay, due to applied electric field, applied electric field. Okay, so whenever you apply electric field, okay, because of this electric field, a force is applied on the charge carriers and charge start moving. Okay, and that they give you drift current, drift velocity and drift current. So this is because of electric field. Okay, now another important thing is, which we know, which generally occurs, we do not see in metals. So that is difference between metal and semiconductor also. That is called your diffusion mechanism. So what is diffusion mechanism? Okay, just 1 minute, give me 1 minute. Okay, so diffusion mechanism means whenever there is a excess charge carriers, okay, whenever there is a concentration gradient, so what happens due to concentration gradient, the charge start moving. For example, if I have a P type of junction, okay, so diffusion mechanism is what? Okay, flow of charge or movement of charge, flow of charge due to concentration gradient, due to concentration gradient. Okay, now for example, if I take a P type of semiconductor, okay, so it has a large number of holes, so I am representing plus by holes. Okay, suppose this is the P type of semiconductor, and here you have some N type of semiconductor which has a large number of electrons. Okay, now whenever there is a charge gradient, okay, so what happens, these charges tend to diffuse. Okay, whenever there are two different type of particles, okay, one is in excess on one side and other is in excess on the other side. Okay, so because of this concentration gradient, this charge will start flowing. Whenever you shine a light on semiconductor in a particular position, if you suppose you're creating holes, so that particular point there is excess of holes, that hole will diffuse from higher concentration to lower concentration. Similarly, if you're producing electron will also diffuse from high concentration to low concentration. Suppose you're forcefully injecting some holes in some point in p-type material, so the excess hole will diffuse. Similarly, if you're injecting excess number of electron, so that electron will also diffuse. Okay, so what happens, so whenever there is a excess hole, okay, so that excess hole will diffuse. Similarly, this excess electron will also diffuse, so they will create a current density. So if I want to create a diffusion current density due to holes, okay, that can be written as diffusion coefficient of holes
Sir,
by
diffuse
dp
means
upon, yes,
diffuse means they move.
yes,
Diffuse is what means here. How whole can move?
diffuse whole movement, whole means like electron recombine with the holes. Okay, generally your electron moves, holes doesn't move. Okay, but if the number is decreasing, we say if electron are moving and recombining, that's we saying the opposite to holes are moving. Now how in p type? Okay, when p type you have a holes and you electron jump to here. Okay, here, so you will be having electron here, you'll be hole, again it comes here, again hole created, again it moves here, electron moves here, you get creating holes. So the whole movement is also described by movement of electrons. Okay, so now if you see here, concentration is high and this side concentration is low, so this dp upon dx is negative. Okay, but current cannot be negative, so what we put, the actual formula for this diffusion coefficient is minus dp upon dx, because dp upon dx is negative. We are moving from higher to lower concentration, so lower minus higher is negative. Okay, where dp is what? Dp is your diffusion coefficient. So dp is diffusion coefficient. Okay, so dp is diffusion coefficient. Diffusion, can you see this one? Diffusion coefficient.
तो dp by dx क्या है? dp by dx.
Charge, the gradient of whole concentration.
Okay, okay.
The gradient of
Yeah.
whole concentration. Okay. Similarly,
जितने होल्स प्रोड्यूस, जितने इलेक्ट्रॉन्स है उतने होल्स प्रोड्यूस हो रहे हैं ना, इलेक्ट्रॉन्स जा रहे हैं इसीलिए तो होल्स प्रोड्यूस हो रहे हैं.
अरे भाई
तो
पी टाइप में तो होल ज्यादा है ना, ये सेम मेटल थोड़ी ना है कि बराबर क्रिएट हो रहे हैं. पी टाइप में होल ज्यादा है, एन टाइप में योर इलेक्ट्रॉन्स आर मोर. सो व्हेन यू कंबाइन देयर एट द जंक्शन, one side is excess of hole, the other side is excess of electron, so they will diffuse. Okay,
so this is for p type.
this is for p type. Okay, p type. Okay, and this is for n type. So I written a p and n type. Similarly, if you have a excess of electron, okay, so because of this excess of electron, what will happen? You have diffusion current. Okay, that is given by dn upon dn by dx. Okay, so here what is actually happening? You again dn by dx is negative, dn by dx is negative. Okay, but then you have to multiply by charge also. So this is negative charge, here you have to apply plus positive charge. Okay, so you are, so we always say current is always in the direction opposite to the flow of charge carriers. Okay, so this is negative. Okay, negative, and but this is also negative, so this will make you positive. Okay, so current direction will be always same. So if I want to write total diffusion current,
सर एक बार वो dp by dx और dn by dx नेगेटिव कैसे है सर, वो थोड़ा सा एक्सप्लेन करिए.
आप बता देता हूँ. टोटल डिफ्यूजन करंट. ओके, भाई dp by ds क्या होता है? dp by ds क्या होता है? ओके, concentration of holes. Okay, p final minus p initial upon distance dx. Okay, now when I'm moving from higher to lower, so my final is lower, na? I'm moving from, suppose here this is higher. Okay, I'm moving from here to here, here is lower, so final is lower and initial is higher, so this will come negative, na? Isn't it?
Yes sir.
That's
Yes
it.
sir, yes.
That's it. Okay, the total diffusion current J diffusion. So this problem happens in semiconductors. Okay, you don't see this in much extent in metals. Okay, so this become Q dn upon dx. Okay, minus Q dp upon dx. Okay, so this is the diffusion current, and we have already seen the drift current. What is the formula for drift current? Drift current density. What is Jn drift?
Any VD.
EVD.
Any Vd, and Vd also we can write what? Mu n e.
Mu into E.
Mu n e. Okay, So this is for drift current. Okay. Similarly, if I write whole diffusion current, that is EP. Okay, so this is a drift current density, and above is diffusion current. So both type of mechanism exist in semiconductors. Okay. Now, what happens? Okay. Now, for example, if I want to show this diffusion, okay, so let me first explain how to represent a p-type of semiconductor or n-type semiconductor. So this is my, say, my p-type of semiconductor. Okay. Okay. So p-type of semiconductors basically represent by the type of impurity. Okay. So here impurity is acceptor. Okay. So I represent this p-type of semiconductor by this minus signs which have hole. So a resultant p-type material is a neutral, but it has a acceptor type of impurities. So acceptors are become negatively charged. Okay. Similarly, if I represent a n-type, either you represent like this p-type material, or you can also represent a p-type material by just holes, because they have excess of holes. Okay. So this is a acceptor impurity. Okay. These are holes. These are immobile charge carriers. They cannot move because they are ion, they are fixed in the lattice. Okay. They are immobile charge carriers. Similarly, this is holes. So you can represent either way to this p-type semiconductor. Similarly, if you want to represent a n-type of semiconductor, so in n-type of semiconductor you have donor impurity. Donor means once they donate, they become positively charged. This is your n-type of semiconductor, which has excess electron. Okay, so this is your n-type semiconductor. Okay, or you can also represent this by excess electron. Okay, electrons. So this is the representation. Okay, how we show secondaries. Okay, this is representation. Now, once we know how to represent this p-type and n-type material, okay, now we can understand the formation of p-n junction. So shall I erase this one? So these are what? Donor impurity, okay, and they are immobile, they cannot move, immobile, and these are electron which can move. So now what happens when I make a contact? Okay, generally we don't bring a p-type or semiconductor and join together like this. Doesn't happen. Generally they are p junctions are formed by diffusion mechanism. Okay, you take a host material, then you first make it p-type, then you diffuse the impurity, and then you make n-type. This way you make junction. But just to understand how p-n junction is formed, okay, what happens in p-n junction when you bring two a p-type of material and n-type material in contact? This is p-type and n-type. So when you bring these material in contact, okay, so this is my p-type material and this is my n-type material. Okay, so now at the contact what happens? Okay, now as soon as I bring them in contact, here we have excess electron. Okay, these excess electron will diffuse in this side. This electron will diffuse in this side. Okay, and these electron will diffuse in the side and they will combine with these holes, isn't it? So once these combine with these holes, what happens? These ions become now negative charge. Now it is this hole is with them. They are neutral. Once electron go here and combine with these electrons, they become negatively charged ions. They become negatively charged ions. So what happens? Okay, here it is p-type material, it is anti-material. At the contact, what happens? At the contact, you have a region which do not have a region. This is called depletion region. This region is called depletion region. Okay, why we call it depleted region? Because it is depleted of free charge carriers. Now it do not have a electron and electron. It do not have electron. Do not have holes. Okay, so this region is depleted of free charge carriers. They don't have a charge carriers. Okay, so once they don't charge carriers, plus there is separation of charge carriers, so there exists an electric field. Okay, so there is a electric field. Now how do this electric field produce? Okay, when this electron will move here, electron will diffuse from here to here. Okay, so this process doesn't continues for forever. Okay, after that what happens? A electric field is produced. This electric field, okay, now it stops further movement of charge carriers. Once the electric field produced, now because these carriers, holes cannot come here. Similarly, electron cannot go here. So at a particular equilibrium, what happens? You have a depleted region, okay, where you do not have a charge carriers, but there is a electric field in the layer. That means you have potential. So this potential should be higher potential, okay, and this should be a lower potential. So I call P region, so P, the N region, so N. Okay, so you have a potential is developed across this barrier. Now let me make you understand what happens at energy band diagram level. Okay, so shall I erase this one? Is this clear?
Yes, sir.
Okay, so now see what happens at energy scale. Now I have a p type of material, okay, which has ECP, and I have a EVP, okay, and I have a somewhere Fermi level of p type material, okay, E F P here, and here I have a intrinsic semiconductor EFI of P. Okay, now if I come here, I have an type of material. So that means here I have ECN and I have a EVN, because the same, we are taking same semiconductor. Okay, so band gap should be same. This energy gap is same. Okay, here I have a Fermi level, okay, which I call it Fermi level of n-type material. Okay, and similarly in the middle, at the middle same level, I have a intrinsic Fermi level of this n-type material. Okay, they are both the same. Now they are both are equal in this position, but I'm representing symbol notation different. Okay, so that we are going to use this one. So now what happens? Now whenever you bring a p-type material, okay, in contact, so at contact what happen? So one material can have only one Fermi level. Okay, so now when you bring two material in contact, okay, so contact should have only one Fermi level. You cannot have a two Fermi level. Okay, if there is a gap, if a difference of Fermi level, there is always flow of charge carriers. Okay, like what happens in metal, you have a metallic wire or metallic rod. Okay, so when you apply a voltage, okay, so this voltage difference create the difference in Fermi levels. This voltage level creates the difference in Fermi level of these ends. Then only your electron flows from higher to lower level, and you say current is flowing in this direction. So whenever you create difference in Fermi level, you tend to flow charges. Okay, that is a current flow mechanism, because you create Fermi level difference. Now here already Fermi level difference is there. Okay, so charge will flow from electron will flow here, more number of electrons, so electron flow from here to here. So here we have electrons, so this electron will flow from n type to p type, like I have shown you in the diagram. They're diffusing, and this electron will move and they will combine with the holes present here. Okay, so what will happen here? Holes are getting reduced, because this electron will come, like I have shown you the diagram. Okay, when these electrons are diffusing and they are combining with these holes, so your holes are decreasing. So when these holes are decreasing, obviously the Fermi level will go up. Okay, so what happens when and similarly here the electrons are reducing. So I told you the Fermi level depends on the concentration of electrons and concentration of holes. If holes are reducing, that means it is becoming intrinsic. Similarly, if your electrons are reducing, that means you is going Fermi level movement should be towards intrinsic region. So what happened? This will go up and this will go down. At the equilibrium at the contact. Now I am drawing the Venn diagram of contact. At the contact, what will happen? At the contact, there should be only one Fermi level. So now at the contact, when they become joined, okay, join means now there's no further movement of charge carriers. So their EFP should be equals to EFN. Okay, and because of movement of charge, there is a potential developed. So potential developed what? Potential is what? Potential, how do you write potential? Potential is what? Electric field is what? Minus dV upon dx, gradient of voltage. Okay, so E is what? E is minus, if I divide by Q, I multiply by Q, this become QV upon dx, and QV is what? QV is the energy level of charge carriers. So this become minus 1 by Q dEI upon dx. Okay, EI is what? Energy levels. These are energy levels. So because you have a potential difference, potential gradient, that means you have energy gradient at the contact. Okay, you have the potential only at the contact. So at the contact you have energy gradient also, dI by dx. Okay, so there is a gradient now.
Sir?
Now what happens? हाँ बोलिए.
What is that, sir? Minus 1 by q into d by dx.
This is electric
Q.
field. B
No,
in
sir.
the which one?
Downward.
Downward. E is
Up.
E
Yeah.
electric field minus 1 by Q QV. I am multiplying by Q and dividing by Q. This
Okay.
QV is become now energy. Okay, so because there is a gradient of potential, there is a gradient of energy levels. Okay, now because we are making joint, so what happens at the joint? 1 minute. At the joint we have a potential difference. That means we have a difference in energies. This potential is called built-in potential. बोलिए.
सर एक बार वो मतलब ना बैंड्स नीचे कैसे चले जाते हैं वो एक बार बताओगे क्या? रिपीट
भाई जब ये इलेक्ट्रॉन्स हैं, भी यहाँ पे जो इलेक्ट्रॉन्स हैं ये यहाँ से यहाँ मूव कर रहे हैं. ओके, होल्स कम हो रहे हैं. होल्स कम हो रहे हैं, इसका मतलब क्या है? इसका फर्मी लेवल ऊपर जाना चाहिए, क्योंकि ये अब कम पी टाइप बन रहा है. कम पी टाइप मतलब होल्स ज्यादा आते हैं तो फर्मी लेवल नीचे आता है. If you have more number of holes, it will come down. If you have more number of electrons, it will go up. Okay, intrinsic, it is middle, so now it will move towards intrinsic. Okay, similarly here also, here you're reducing electrons, so it will come down and it will move towards intrinsic. Okay, and at the contact they should be on one Fermi level, one material, one Fermi level. They should not be gradient of Fermi level. Okay, so there is no gradient of Fermi level, but since there is a potential, so there is a potential here. Okay, so there is a potential difference, there is electric field, there is a potential difference, there should be a gradient of energy level using this equation. Okay, and this potential, what I have shown you in the diagram, where you have this PN junction, you have P, this is you have N, so you have here minus, okay, this you have plus, minus, plus, minus, plus, minus, plus. Okay, so this you have electric field here, and this is the potential difference. Okay, so you call this is VP, you call this is VN. Okay, so difference is a potential difference. This potential difference is called your built-in potential. I call it VBI, QVBI. Okay, now if I draw here the intrinsic level is like a scale. Okay, that is not a actual Fermi level. So this is your EFN, EFP, EFIP, intrinsic, EFIP, and here also this is the middle, that is called your EFI. Are you getting? EFIN. Okay, now this difference between these two levels, okay, in these two levels, okay, Fermi levels, it is called your QVBI. So this level and the difference of these two levels is called your QVBI. So same amount of जितना ये ऊपर जा रहा है उतना ये ऊपर जा रहा है. Okay, so this gap, okay, the difference between now in this position is equal to your QVBI. Now we can calculate QVBI by using this definition. Okay, there is a many method to calculation of QVBI. Okay, at least 4 to 5 way we can derive the formula for VBI. So now this is a p-type material. Okay, so in p-type material you have a number of holes. Okay, in p-type material is equals to Na, we know. Okay, and number of electrons in p-type material we know it is Ni square upon Na. Okay, similarly in n-type of material you have number of holes in n-type material is equals to Nd, and number of holes in p-type material is Ni square upon Nd. Okay, this is an equilibrium. Okay, now let us see what happens when we make them join. Okay, so whenever we make them join, okay, now what I found, so whenever I join them, okay, so what happens, I create a potential difference. Okay, so from here to here, okay, there is a potential difference. Okay, at the junction you have a potential difference. So this is your Vn and this is your Vp. Okay, this is your Vp. Okay, and the difference of this Vn by Vp is called your VBI. This is your VBI. Okay, now I want to calculate this VBI. So since there is a potential, there is an electric field also, so we have to plot electric field also. So for the moment I am only plotting this potential. Now I want to calculate what is the value of this VBI. Okay, so this is very simple. Okay, so if you return, I can draw this, I can erase this one, and we can calculate the built-in potential. So put the heading built-in potential. So shall I erase this one? So now put the heading built-in potential. Okay, so now I know the position of Fermi level in p-type semiconductor is given by EFI of P, okay, plus KT ln Na upon Ni, isn't it? This is the position of Fermi level, okay, of p-type material. And in n-type material, the position of Fermi level is given by EFN, EFIN minus KT ln ND upon NI. Okay. Now when you make join at the junction, my EFP should be equals to EFN. Okay, make them equal and calculate the built-in potential KT by Q. Okay, this is KT by Q. KT by Q or KT? What is the formula?
KT.
KT.
Only KT, na?
Yes, sir.
Okay, it's only KT. So now find the difference. I want built-in potential. So built-in potential is like, we know the energy difference QVbi is equals to what? EFIP minus EFIN. In the diagram you have seen the difference between here. Okay, difference between this EFIP and FIN. This is equal to built-in potential EFIN. Okay, this difference is called your QVbi. Okay, now let me calculate this one QVbi. Okay, so when I put these values, you make them equal. Okay, so what happens? Put these values here. Okay, so when you put these values here, what you get? You get, इसको erase कर दूं. Okay, so if you put these values here, you get QVbi. Okay, if you put the value of EFI, okay, so EFI is nothing, it is a KT upon ln Na upon Ni. Okay, and then minus plus KT ln Nd upon Ni. Okay, EFI and EFI will cancel because both are same. So now I can write my VBI is equals to KT upon Q. Okay, and this is ln. If I add this ln, I can write Na ln A plus ln B, ln AB. Okay, Nd upon Ni square. Okay, so this is the formula for
साइन आ रहा है सिर्फ
हाँ?
एक्सप्रेशन नेगेटिव साइन आ रहा है एक्सप्रेशन में
सर एक माइनस
माइनस है ना इधर.
प्लस आ रहा है साइन
हाँ, तो प्लस होता आएगा. ये आ रहा है क्या, चेक करो. ठीक है, इज इट करेक्ट?
सर उल्टा ln Ni square upon Na and
ऐसे कैसे आएगा, माइनस कैसे आएगा? EFI हाँ?
ये फॉर्मूला में ऐसा है ना EFP is equal to EFIP plus KT
अरे
Na upon
ये EF इंट्रिंसिक है,
हाँ सर
तो EF इंट्रिंसिक क्या आएगा? EF इंट्रिंसिक क्या आएगा आपका? EFP ना? हाँ, EFP
प्लस KT
प्लस और माइनस.
प्लस
माइनस आएगा भाई, माइनस
माइनस है सर.
माइनस आएगा ना. KT अपॉन ln Na upon Ni square. Okay, and similarly if I calculate EFIN, okay, that will become EFN plus
KT log ND by NI.
and Ni square. Okay, so now I want if I got difference, it should come minus coming. Huh? Okay, just let me check. Minus, how can it come minus?
So now in this case it will be correct. Earlier we have written different formulas. That's why this is coming.
Just wait, मुझे check करना दो ना, मेरा भी तो आना चाहिए. Okay, so if I write D is equal, okay, this so EF5, तो EF5 में क्या होता है कि नहीं, EF5 में आपका पॉजिटिव आएगा ना भाई. EF5 तो नीचे होता है ना, फर्मियल्स के नीचे होता है ना. EF5 भी आपका EFP क्या होता है? EFP इज माइनस KT. EFP होता है वो EFI के नीचे होता है ना. आर यू गेटिंग? और जो EFN होता है वो EFI के ऊपर होता है, तो यहाँ पे ये करेंगे तो इसका ये पॉजिटिव आएगा और इसका करेंगे तो ये नेगेटिव आएगा।
सर उल्टा ही आएगा।
अरे भाई
नहीं सर, अब सही है, इससे सही है।
अब सही
अगर
है
ऐसे लिया ना तो VBI का
हाँ
फॉर्मूला नेगेटिव ही मिलेगा।
हाँ अभी सही है। ओके नाउ यू हैव दिस फॉर्मूला।
नेगेटिव
ओके नाउ EFI minus PA you get plus KT by Q lambda। ओके चेक इट, सही कि नहीं आ रहा अभी? उसमें सही कर देना, उसमें वो EFI के नीचे है। ओके दिस इज माइनस एंड EN दिस इज पॉजिटिव, दिस इज प्लस, EFI plus। I have written making understanding this is like a band gap of EC, band edge EC. You can write in terms of EC also. Okay, you can find the difference of this EC also. Okay, you have EC, ECN, and ECP. You can find the difference of this also. Then also you get same QVbi. So this is the formula for built-in potential.
हेलो
Okay.
सर, अभी जो लिखे वो फॉर्मूले यूज करने हैं ना,
हाँ ये वाला, हाँ जो अभी लिखे हो अभी यूज करना है।
EFI
हाँ वो तो मैंने कल निकलाया था ना,
आ रहा है।
वो तो याद होनी चाहिए ना भी। फर्मी लेवल तो EFI के ऊपर होगा एन टाइप में, पी टाइप के नीचे होता है तो माइनस आएगा, केटी आएगा, केटी आएगा। ओके हाँ ओके सो दिस इज योर फॉर्मूला। एनी इशू, एनी प्रॉब्लम कंचन?
VBI के फॉर्मूला में नेगेटिव आ जाता है अगर ये फॉर्मूले यूज किए तो, मतलब मेरा
नेगेटिव कैसे आएगा भाई? अभी तो मैंने लिखा फॉर्मूला, अभी तो नेगेटिव कैसे आएगा? EFI ये EF इंट्रिंसिक है भाई, EFP नहीं है।
हाँ सर,
तो EF में तो प्लस प्लस आएगा ना। अभी जो मैंने फॉर्मूला लिखा EFP क्या होता है? EFIP
KT
minus KT ln Na upon Ni।
NI
तो ये Fermi intrinsic, it is below the intrinsic, Fermi level is below the intrinsic level. So I want, if I want this one, this will go there, this will add, na? This will become add, this will become EF plus this one, and EFP and EFN are equal. Are you getting now?
ओके सर, आई विल ट्राई।
सर।
हाँ बोलिए।
सर अब क्लियर हो गया सर।
हाँ हो गया ना। ओके
पहले वाले फॉर्मूला से नेगेटिव आ रहा था, अब ठीक है।
हाँ वो साइन का प्रॉब्लम है ना, साइन का इशू है ना, विद द साइन इशू। सो नाउ दिस इज योर KT by Q ln Na upon ND Ni square. Okay now you can see VBI depends on carrier concentration and carrier concentration depends on band gap. So more the band gap, okay, if you are making PN junction out of higher band gap material, then VBI will be what, low or high? High, because this will be low. If I take gallium arsenide and if the band gap of EG, the band gap of gallium arsenide is higher than the band gap of silicon, is higher than band gap of
Germanium.
germanium. Okay, so your Ni is lower. Ni is lower of this one, this material, than this material, Ni of silicon, Ni of gallium arsenide, and Ni of germanium. So Ni of germanium is highest. So VBI is opposite. VBI is higher. VBI is higher for gallium arsenide. So your VBI for gallium arsenide is higher than VBI of your silicon, is higher than the VBI of your germanium, because they have lower concentration. Okay, so they have a higher VBI. So built-in potential. Yes.
VBI में यदि NI को छोड़ दें तो
हाँ
बाकी सारी टर्म्स कांस्टेंट है।
हाँ भाई पी टाइप की इम्प्योरिटी आपको पता ही है Na। ओके एन टाइप की इम्प्योरिटी आपको पता ही है
पता ही
Nd।
है ND।
हाँ सो वो तो डोपिंग हम कितना करते हैं उस पर डिपेंड करता है ना, कंसंट्रेशन डोपिंग कितना है। Ni स्क्वायर इज अ मटेरियल पैरामीटर,
इनवर्सली प्रोपोर्शनल।
Ni is the intrinsic carrier concentration which depends on temperature for any given material. Okay, now let me write some more formula for VBI. Just now we have seen that VBI is equals to KT upon Q ln Na upon Nd Ni square. Okay, so what you can write now, you know that your if I want to convert this formula in other formulas, okay, I want to bring in carrier concentrations. KT upon Q ln Na upon Ni square upon Nd. Okay, so I know what is this one. I can write KT upon Q ln what? Na is what? Na is holes in p-type material, and this is what? This is what? Holes in n-type material. Okay, so this is the ratio of majority charge carriers to minority charge carriers. Na is what? Na is what? Na is your holes in p-type material. Okay, and Ni square upon Nd is your what? Holes in n-type material. So you can write this VBI formula in this form also. Okay, are you getting this formula?
Yes.
Okay, similarly, if you want, you can also write VBI in other form. You can write KT upon Q. You can put ND above, and you can put Ni square upon Na below. Okay, so now you can, this formula become KT upon Q. Now this ND is what? Concentration of ore. Yes, NN by NP. Very good. Okay, so these three formula of VBI you must remember. You may be given any values. Okay, of course you know this thing, so you can find automatically. You can find these things. Okay, there is no issue. If you know this thing, you can find, you can convert in this formula. If you know this, you can convert in this formula. But I am writing in different forms. Okay, so that it will be easy for you if you want to learn sometimes. So this is your formula for built-in potential. Okay. Now, if there is a potential, there should be electric field. Okay, and we have already told there is a depletion region, we have electric field. Now I want to calculate that electric field. Okay, so put the now heading. The junction, what we are doing, this is called your abrupt VN junction. Okay, abrupt VN. What I tell you, what is the abrupt VN junction? So now electric field. I want to calculate my electric field value. So electric field, okay, in PN junction. So I want to calculate electric field in PN junction. Okay, I have this PN junction. I have P junction. I have N junction. Okay, here I have minus ions, and here I have plus ions. Okay, so this is called P side. Say this is XP minus XP. Say this is the 0, and say this is XN. Okay, the boundaries I am defining XP 0 XN. Okay, and this total is called the width of depletion region. Okay, so the width W is equals to XN plus XP. Okay, so this is the one thing. Okay, now what do you mean by, I call this junction is called abrupt PN junction. This type of junction is called abrupt PN junction. Okay, so why this junction is called abrupt PN junction? So you see, one side of the junction you have a negative charge, and suddenly when you move to the boundary, suddenly you get plus charge. Are you getting? Okay, so if I want to write how much charge is present here, okay, how much charge is present, so how can you write the charge? What is charge? So if you want to write charge, okay, so charge is here, you have a, say charge is Q. Okay, what is the concentration of these ions? What is the concentration of these ions? Na in P side, Na. Okay, if I say the cross section area of this one, so this Na is what? This Na is what? Na is the concentration per centimeter cube. Concentration per centimeter cube. Nd is also, okay. Nd is a donor concentration. Okay, donor concentration per centimeter cube. This is the acceptor concentration per centimeter cube. So if I want to, how many charges present are there, so I should know the concentration of acceptor and donor. So here concentration of N is Na. Okay, concentration charge per centimeter cube. If I multiply by volume, if I say the cross section is A, okay, and this width is xp, so this become your charge on p side, isn't it? Similarly, if I write charge on n side, I can write what? Q nd, nda and xn. Are you comfortable with this form, these expressions? Are you writing how I'm writing this expression?
Yes,
सर
sir.
एक साइड माइनस आना चाहिए ना?
वो चार्ज में लिखा है ना, चार्ज माइनस में लिख दूंगा अपने आप ही.
Yes
ठीक है?
sir.
क्यों लिखा है? So this I am just taking magnitude of charge. Okay, so here minus charge plus charge. Magnitude is same.
Yes sir.
Both side magnitude is same. Okay, so if I cancel this thing q n a, so what I get? Na xp equals to nd x1. Okay, so this is called charge neutrality condition. This is called charge neutrality. Charge neutrality. Okay, at p-n junction. So now what do you mean by a abrupt p-n junction? So abrupt p-n junction का मतलब है कि if I draw the charge density, okay, पहले इसको लिख लो, बताता हूँ. If you have written this one, let me, I can erase this one. This is called charge neutrality condition. So both sides you have a same charge. Now suppose if I increase this Na, if I increase Na, then what will happen? You have Na xp equals to nd xn. Okay, now I'm assuming the concentrations are same. If I increase Na, if Na is become greater than nd, then what will happen? Xp will decrease or xp will decrease or increase?
Decrease.
Decrease. Very good. So this is called your symmetric junction. When Na and Nd are in same order, okay, if Na and Nd are same order, then this width is called, this depletion region is symmetric. This is called symmetric. Symmetric with respect to origin. Now, if you increase Na, if you increase the concentration here, so what become, this width will decrease. Okay, so now this is symmetric junction. Now suppose I am increasing Na. Now if I increase say Na, okay, so when I increase this Na, so what will happen? But depletion width will decrease. So if I'm increasing this Na, and this is say my origin, okay, so this is my say minus, okay, and then all this xp will increase. So this xp will become plus, okay, because the total charge should be same. Total charge at the interface should be same. So if I'm increasing the concentration here, so this is for Na is greater than Nd. So this become minus xp, this is xn. So this width will decrease. Okay, wherever is more doping, that width will decrease. Similarly, opposite thing. If I have a like this p type, n type, okay, and suppose this is my origin, this become xn, and this become minus xp. Okay, so this become minus, and this is plus, this is plus, this is plus. Okay, this is the case for when nd is greater than na. So wherever you will increase the concentration of dopant, okay, that side width will decrease. If they are same order, then that is called symmetric p-n junction. Okay, and this is called asymmetric p-n junction. So wherever is doping is high, that side your width will decrease. Okay, is that point is clear to you? This from charge neutrality. Okay, this I have done from charge neutrality condition. Is that clear?
Yes, sir.
Yes sir.
So now let me, okay, write the what is abrupt p-n junction. Okay, Now I want to write abrupt p-n junction. What is abrupt? Why we call this junction as abrupt p-n junction? Abrupt p-n junction. So I call it abrupt p-n junction because there is a sudden variation of charge density. If I plot charge density curve here, density versus x. Okay, so this is my n type and this is my p type. I'm plotting resistivity, this charge density. So here we have plus charge in n side we have plus charge. So charge density is what? Charge density is charge into concentration of dopant Q and D. This is charge density. If you multiply by volume, it will become your charge. Similarly, this side of minus side, if you go to p side, okay, you have minus charge, and the charge density is called QNA. Okay, so you have a sudden jump of charge density from positive to negative. Okay, that's why this is called your abrupt p-n junction. Abrupt p-n junction. Okay. Now I want to calculate electric field inside. हाँ बोलिए.
ग्राफ एक बार और बता दीजिए.
ग्राफ हमने पीएन जंक्शन ड्रॉ किया ना अभी. वी हैव दिस पीएन जंक्शन. तो एन साइड पे क्या प्लस है कि माइनस है? एन साइड पे क्या है चार्ज? प्लस है कि माइनस है? या क्या है? प्लस है कि माइनस है?
प्लस है सर.
प्लस है तो मैंने प्लस तो किया है क्यू एन डी. यहाँ पे क्या माइनस है?
माइनस है सर.
माइनस. So this is concentration. Okay.
Yes sir.
Ion per centimeter cube multiplied by charge. Atom per centimeter cube multiplied by charge. This becomes charge density. Okay. So this is a charge density curve for abrupt p-n junction. Now I want to calculate electric field. Okay. Let us calculate electric field. Okay. So electric field, in order to calculate electric field, okay, so this is my charge density profile, okay, Q and D, and this is my minus QNA, this charge profile, okay, X. Now I want to plot the electric field, okay, electric field versus X. I want to plot my electric field versus X, okay. So how can I calculate the electric field in P side and N side? Okay, so if you want to calculate the electric field, I should apply what? Poisson's equation. Whenever there is a field, okay, whenever there is charge bounded in region, some region, okay, you can calculate the electric field. So Poisson equation says what? Del square phi equals to what? Minus rho upon what is the Poisson equation?
2 epsilon naught
rho by epsilon 0.
Okay, epsilon. So here what is I write ES semiconductor. Instead of E naught, I will write the permittivity of semiconductor. Okay. Now I know electric field. Electric field is what? If I write this in one dimension, I'm going in moving one dimension. So I can write this is a del phi upon del x square equals to minus rho upon EC. Okay, and I know that electric field is minus del phi upon del x. Okay, so here what I can write, if I put this value here, I can write dE by dx is equals to rho upon ES. Okay, so now if I want electric field, I can integrate this equation. I know charge value both sides. This side is Q and D, this side is minus Q and A. I also know the boundary condition. What is the boundary condition? Boundary conditions are that at x equal to xp, okay, and x is equal to xn, the electric field is 0. Here there is no field in this side. Similarly, this side there is no field. So this is plus, this is junction, and this is minus. So electric field is only in the junction at boundaries x equal to xn and x is equal to minus xp. There is no electric field. Okay. and I can find electric field by dx by dx. Okay, rho by es. Now this is what d by dx. This is the slope of electric field, and this says if I said p side we have positive charge, the slope is positive. Okay, at the boundaries you have a zero electric field and the slope is positive. So if I want to plot electric field, I can put like this. This is for p, this is for n side, this is for n side, for n side. Similarly for p side, this is equals to q n d upon es. For p side, I can calculate d by dx. We'll calculate tomorrow. I'm just showing by slope. Okay, es, this is minus q n a upon es. Now this d by dx is negative, and at the boundary it should be 0 at xp, and it should negative slope. So this is your profile of electric field inside the p-n junction, and this is called your maximum electric field. So tomorrow we will derive the exact formula, exact formula of this maximum electric field and field equation in p side and n side. Okay, so for the moment I have just directly written. Okay, I know this, my d by dx is rho by epsilon 0. So I know the charge density, I know the boundary condition here is 0, electric field is 0, here electric field is 0, and d by dx, okay, d by dx should be positive, so this is slope, he should be negative, both should match at the center. So this is for profile of electric field. Okay, so we'll discuss this in detail tomorrow. Okay, for the moment I'm stopping here. Now any question is there, you can ask. Ask any question is there from this part. Okay, if there's no question, then I can stop. Kanchan, any question?
No, sir.
Okay.
सर ये जो DE by DX for n टाइप के लिए ड्रॉ किया है,
हाँ
ये नेगेटिव पॉजिटिव है ना?
हाँ पॉजिटिव है ना, तो ये स्लोप पॉजिटिव है, नेगेटिव स्लोप क्या होता है, पॉजिटिव स्लोप क्या होता है, ये पॉजिटिव स्लोप है, दिस इज पॉजिटिव स्लोप. Okay, this is negative slope. How do you plot y equal to mx? Y equal to mx is like this. Okay, and y equal to
Yes.
minus mx is like this. Okay, when the slope positive like this and you go down, if you go like this, so this is your minus slope, this is a positive slope, both electric field should be 0 at boundaries. Okay, then somewhere it should be maximum. So we'll discuss in detail tomorrow. Okay, any other question? So I'm stopping here. Thank you very much.
Thank you, sir.